Hello everyone. Today is October 24th, 2025, Levy Friday. And you know what that means. It's time to pull a trending article from the archives. Let's see what we've got today. Oh, this one looks pretty cool. It's about making AI for audio way more flexible. Nah, less of a pain to use. The title is AMAuT, a flexible and efficient multiview audio transformer framework trained from scratch. The curl is Nave to effect 10.19,368 on. Okay, so let's break this down. What's the big problem this paper is trying to solve? Well, you know these huge, super smart AI models that can understand audio? Things like HuBERT and Qwen-Audio. They're amazing, but they have a secret, kind of annoying problem. They're all pre-trained on gigantic mountains of data, which takes an insane amount of computer power. We're talking days or even weeks on hundreds of pumps. Because of this massive pre-training, they get really picky about the audio we give them. They demand a fixed sample rate, like exactly 16 kilohertz, and a fixed audio length, say, exactly 1 second or 10 seconds. If your audio is different, maybe it's longer, or recorded with a better microphone at a higher quality, you're out of luck. You then have to downgrade your audio, which loses information, or you have to retrain the whole giant model, which is, super expensive. It makes these powerful tools really inflexible and hard to reuse for new projects. So this paper introduces a new hero called AMAuT, that stands for Augmentation-driven Multiview Audio Transformer. The core idea here is revolutionary with a quiet, nerdy way, instead of relying on that massive retraining. AMAuT is designed to be trained completely from scratch for each specific task. This makes it incredibly flexible. It can handle pretty much any sample rate and any audio length you throw at it. No more criticizing or downgrading your files. And the best part? It's insanely efficient. The paper says it achieves top-tier results while using less than 3% of the crew hours needed by those pre-trained models. That's a huge deal. So how does it actually work? It has a few clever tricks up its sleeve. First, there's something called Augmentation-driven multiview learning. Sounds complex, right? But the idea is simple and brilliant. In training AI, instead of showing in an audio clip just once, AMAuT creates several slightly different versions of that same clip on the fly. Like one version might be shifted a little in time, another might have a tiny bit of background noise added. The AI then learns from all these different views at the exact same time. This forces the model to learn what's truly important in the audio, making it way more robust and better at handling real-world imperfections. It's like learning to recognize a friend's voice not just in a quiet room, but also at a noisy party. Next, it has a flexible CNN bottleneck. This is how it handles audio of any length. It first turns the audio into an image called a spectrogram. Then this special part of the network, the CNN, acts like a universal adapter. It takes this spectrogram, no matter how long it is, and cleverly squishes it down into a fixed-sized chunk of information that the main part of the AI can understand. Oh, and here's a neat little detail. Inside the AIM's brain, it uses something called dual or pulsatile tokens. Most models like this just have one special token at the beginning of the data, to kind of summarize everything. And AMAuT adds a second one at the end, a tail token, by looking at the audio from both the beginning and the end simultaneously. It gets a much richer and more complete understanding of the context. And finally, it has a cool feature for when it's making predictions, called test-time adaptation or augmentation or touchwell. Even after it's fully trained, right before it gives you an answer, it can quickly fine-tune itself to a specific audio it's listening to. It also creates a few slightly altered versions of the test audio. It's a prediction for each one, and then averages the results. It's like double-witching your work, which makes the final answer more reliable. Okay, so this is all really cool tech. But what can we actually do with it? Let's think about some real-world applications. First, music. Imagine a music recognition app like Shazam but on steroids. The AI that could instantly identify any song. They even classify its genre or mood, regardless of whether you're playing a 15-second clip from TikTok, recorded at a low quality, or a full 10-minute high-fidelity track from an orchestra. Because it's so efficient, this could all happen right on your phone, without needing to send tons of data to the cloud. Second, voice technology and accessibility. Think about voice assistants like Siri or Alexa, or real-time transcription services. People speak at different speeds and their voices are recorded on all sorts of devices. From cheap laptop minis to professional studio equipment. AMAuT's flexibility means it could build a voice command system that works reliably across all these different conditions without any extra hassle. This would be amazing for accessibility tools, helping to accurately transcribe speech for people with non-standard speech patterns in their video games. Sound design is everything for immersion in games. AMAuT could be used to classify and data sounds in real time with very little processing power. For example, it could tell the difference between footsteps on grass, gravel, or wood, or identify the exact weapon being fired just from its sound because it's so lightweight. It could run on a gaming console or even a phone without causing any lag, making games more dynamic and realistic. So how does this stack up against the breed for trained models? Well, it's a different philosophy. The big models are like a scholar who has spent decades reading every book in a giant library. They know that they're a bit set in their ways and expect everything to be just so. And that, on the other hand, is like a brilliant fast learner that can master a new subject just by reading one textbook. It's way more adaptable and gets up to speed much faster. The results show that AMAuT gets performance that is comparable, and sometimes even better than the big guys, while using a tiny fraction of the computational resources. This basically democratizes high-performing audio. You no longer need access to a supercomputer to build state-of-the-art audio tools. You know, it makes me think. Why did the audio transformer break up with the spectrogram? Because it felt like it was being put in a box. Get it? The fixed-size patches. Okay. Tough crowd. Anyway, the big takeaway here is that AMAuT is a huge step forward. It shows that we can build AI that is not only powerful, but also flexible, efficient, and accessible. By training from scratch and using these clever architectural tricks, it opens the door for all sorts of new applications and environments where computing resources are limited. It's a really smart and practical approach, and I'm excited to see where it goes.